before going for the splitting of octahedral, let's see the splitting of d orbitals in tetrahedral complexes. So before understanding how the splitting has been done, let's see the structure of tetrahedral. This is the tetrahedral structure. You can see this is the cube. This is the cube. The corners of the cube are in this way. And you can consider one of the axis as x-axis, one of the axis as y-axis, and one of the axis as z-axis. So in this cube, 1, 2, 3, 4. 4 corners of the cube are being occupied by the ligands in the tetrahedral splitting. So the approaching of ends will be in this way. So it is towards the axial, so the approaching of the ligands in the tetrahedral geometry is towards these points. So whatever the orbitals are there in the approaching areas of the ligands, those orbitals will exert the higher energy in the d orbital. That means the splitting will be done in such a way that along the axis or in between the axis, if the ligands are coming approaching towards the metal atom, the orbitals which are there in between will show the higher energy level. So the T2G and EG groups will split in such a way. Let's see the splitting. This is the d orbital. D orbital, the free metal ion. This is the energy. Then this is the force influenced spherical force, spherical electrostatic force influenced. So the spherical field is being created. So the energy is increased. From here, it will split into the non-axial and the axial. That means this is EG, this is T2G. So EG will show the lesser energy than the degenerated d orbitals, and T2G will show the higher energy than the degenerated d orbitals. Why it is showing the higher energy? Because the ligands are approaching in this direction. The non-axial plane will approach in the non-axial plane, the ligands will approach in the non-axial plane, so that the T2G energy levels will increase. The EG energy levels will decrease further than the degenerated orbitals. That is called as the barycenter. Barycenter is the energy level with the spherical field. From the barycenter, the EG, the energy level will decrease, and T2G energy level will increase. And it is said that it is 2 by 5 of delta, it is 3 by 5 of delta. Delta is the crystal field stabilization energy. For tetrahedral complex, it is delta T means tetrahedral crystal field stabilization energy. So because it is going upwards, because we have 5 orbitals, so 2 by 5 of the delta T will be increased for the T2G, and 3 by 5 of the delta T will be decreased to the downwards than the barycenter. So this splitting of orbitals will purely depends on how the ligand is. How the ligand is. Because the ligands have strong field and weak field ligands. Weak field ligands and strong field ligands. Strong field ligands are those ligands which will split the d orbitals in such a way that strong field ligands will split the d orbitals in such a way that the maximum splitting should be done, and the weak field ligands will split the d orbitals, or sometimes they cannot able to split the d orbitals, and the energy between these two will decreases. So now we will write the spectrochemical series of these ligands. So from the weak field I will start, that is I minus, Br minus, S minus 2, Cl minus, NO3 minus, F minus, OH minus, ET, ethyl alcohol, ETOH, and oxalate, the neutral atom, the neutral molecule, and H2O, the neutral molecule, and NCS, and EDTA, and NH3. NH3 and pyridine will show the equal kind of splitting field, or strong field or weak field energy. And then EN, then dipyridine, then orthophenolphthalein, then NO2 minus, Cn minus, and CO. So from here, I minus, Br minus, and S2 minus and Cl minus are the weak field ligands, and they will fail to split the d orbitals. And CO, Cn minus, and NO2 minus very strongly they will split the energy levels of T2G and EG. Now we will see the strong field and the weak field ligands, how they are splitting the d orbitals.